Pre-Calculus Lesson 4.1, Reviewing Right Triangle Trigonometry. You've used this trigonometry before in geometry and also a little bit in Algebra 2. The learning targets that we're focusing in this video clip are: can you find the values of the angles of right triangles? Can you solve right triangles? And in the next clip, which either could be today for you or tomorrow, depending on what I put in Skyward, I can use the angle of elevation and depression to find the distances. There are 6 trigonometric ratios. You know of 3 from when you were in geometry. When we talk about trigonometric ratios, we're talking about the ratios with respect to an angle. So here's theta. Theta is like a circle with a horizontal line through it. And theta is our angle. With respect to this angle, the hypotenuse, the longest leg, is always the hypotenuse. And we're talking about 6 trigonometric ratios with respect to a right triangle. So we have the hypotenuse, the leg across is called the opposite leg, and the one that's touching the angle but isn't the hypotenuse is the adjacent leg. So many of you may remember the expression Sohcahtoa. Because the sine of the angle was defined as the ratio of opposite over hypotenuse. The sine of an angle is defined as the opposite over the hypotenuse. The cosine of an angle is defined as the adjacent over the hypotenuse, the length of the adjacent side over the length of the hypotenuse. That's a ratio. And lastly, the tangent is defined as the opposite over the adjacent. Tangent of this angle would be this side over this side, the opposite over the adjacent. There are 3 reciprocal ratios. So when I say 3 reciprocal, we're looking at the reciprocal functions. So here's the trigonometric functions, you know, sine, cosine, and tangent. Well, this reciprocal function for sine is CSC. By the way, this is actually spelled sine with an E, but we abbreviate it SIN. This is spelled cosine, but we abbreviate it COS. And this one's spelled tangent, but we abbreviate it TAN. This one, the reciprocal for sine, is cosecant. So how do I find it? Well, if I know the ratio for sine, so if I found the opposite over the hypotenuse, I just take the reciprocal value of that fraction. And I have cosecant. It's called cosecant. The reciprocal of cosine is called secant. It's abbreviated SEC. It is called secant. Since cosine is adjacent over hypotenuse, secant is hypotenuse over adjacent. And lastly, tangent, which was opposite over adjacent, its reciprocal function, cotangent, oh, I spelt it out by mistake, cotangent of theta is adjacent over opposite. And they truly are reciprocal values. They're functions. If you know the angle, there is an associated ratio that goes with it for all similar triangles. And you talked about that a lot in geometry, but it's been a while. So I want to take a quick detour from this, and you can either find spot on like the top of the page or on another sheet of paper, but there's some special right triangles that you are supposed to know the values of from geometry. We hit it pretty hard in geometry, but again, for some of you, it's been a while. So with respect to these special right triangles that are used all the time in architecture and that we use to get exact values, we use them with the unit circle. We will be using them later basically all year. But we're going to memorize them a different way. We have an isosceles right triangle, which means each of these angles is 45 degrees. And that means that these 2 legs are the same. They're 1 and 1. And the hypotenuse is the square root of 2. Some of you memorized formulas to solve this, but most of you solved any triangle that was a 45, 45, 90 triangle, whether it was this size or something that had sizes of 10, 10, then this would be 10 square roots of 2. These triangles are similar. So no matter what I do, the sine of 40, or the tangent of 45 degrees, tangent is opposite over adjacent, tangent of 45 degrees is 1. If I were to ask you to find the cosecant of 45 degrees, well, you'd first look at the sine. The sine of 45 degrees is opposite, remember sine is so, opposite over hypotenuse, 1 over square root of 2. Now, if I were finding sine, I would have to rationalize this. But since I'm not finding sine, I'm rather finding cosecant, I just have to flip it. Square root of 2 over 1 is the cosecant of 45 degrees. This is a special right triangle. It's the 45, 45, 90 triangle that you memorized in geometry. You will see it and use these values, these 6 trig values, primarily these 3 though, a ton. So you may want to rememorize this triangle. It will come in handy in the next few sections. We also had from geometry the 30, 60, 90 triangle. And it came from an equilateral triangle where we bisected the equilateral triangle. So all these angles had been 60, but now this was 30. On our equilateral triangle, this, which is now our hypotenuse, was a length of 2, which meant that when we bisected the equilateral triangle, or cut this side in half, this short leg is 1. And if we do Pythagorean's theorem, 2 squared is 4, minus 1 squared, which is 1, is 3. Take the square root. This long leg is the square root of 3. You also were expected to memorize and use this triangle in lesson 5.8 of geometry to solve similar triangles that were special right triangles, 30, 60, 90, or 45, 45, 90. This will come in handy when they ask you problems like find the exact value of the cosine of 30 degrees. Well, the cosine of 30, cosine Sohcahtoa, is adjacent over hypotenuse. So here's my 30 degrees, here's my adjacent, here's my hypotenuse. Adjacent is touching, so this is square root of 3 over 2. And lucky us, we don't have to rationalize this. However, if they had asked for the secant of 30 degrees, we would do the reciprocal value, 2 over square root of 3, and we would have to rationalize it, giving us 2 square roots of 3 over 3. So just a brief recall there, you need to know these triangles. 45, 45, 90, the legs are 1, the hypotenuse is the square root of 2. On the 30, 60, 90, the short leg is 1, the hypotenuse is 2, the long leg is the square root of 3. Some people put these in the wrong spot, but square root of 3 is less than 2, so, and the hypotenuse has to be the longest side. So just be aware of that. Because you will see some of these later when I ask you to find the exact value of a 30, a 60, or a 45 degree angle for any of these 6 functions, 6 trig functions, you will have to draw these triangles for now to find those values. If you use your calculator, it will give you the decimal approximation, not the exact value. Exact value is synonymous with simplified, or not synonymous, but the same as simplified radical form, which means I have to write it as a fraction with simplified radicals, no radicals in the denominator, and all fractions simplified. Let's move on to example 1. We're asked to find the 6 trigonometric functions of theta. As I find sine, I will flip it to get cosecant. As I find cosine, I will flip it to get secant. As I find tangent, I will flip it to get cotangent. So with respect to this angle, theta, that's the letter, Greek letter that we use to represent angles, the sine of theta, and all they want is the ratio. I'm not solving anything. They asked for the exact values, the ratio values, finding the values of trig ratios. They're not asking me to solve for a side. They're not asking me to solve for an angle. That's going to come later. Sine of theta equals, remember, Sohcahtoa. Sine is opposite over hypotenuse. So in this case, it's 5/13. Not bad. I don't even have any radicals to rationalize, and 5/13 is already reduced. That means that cosecant of theta is 13/5, the reciprocal value. Cosine of theta then is the adjacent over the hypotenuse. Adjacent to theta, or touching it, is 12, and the hypotenuse is 13. So this is 12/13. The secant, which is the reciprocal of cosine, would be 13/12. And lastly, for this problem, we begin with the tangent of theta. Tangent is opposite over adjacent, so 5/12, which means cotangent of theta is 12/5. I personally don't memorize these ratios. You're welcome to. I strictly memorize that cosecant is the reciprocal of sine, secant is the reciprocal of cosine, and cotangent is the reciprocal of tangent. So I only need to know Sohcahtoa to be able to find all 6. For our next triangle, once again, it was very nice they gave you all 3 sides. A lot of times I don't do that. They didn't do it in geometry. We often would give you only 2 of them, and you'd have to use Pythagorean's theorem to find the third in simplest radical form. But for this quick example, the sine of theta is the opposite over the hypotenuse, 21/29. If I could reduce this fraction, I would, but nothing will go into 21 and 29 except for 1. This means that the cosecant of theta is 29/21. The cosine, defined as adjacent over hypotenuse, remember Sohcahtoa, adjacent over hypotenuse, the adjacent is 20, the hypotenuse is 29, 20/29, which means that the secant of theta is the reciprocal value 29/20. Again, if these fractions were able to reduce, I would reduce them. And lastly, for this problem, the tangent of theta, which is opposite over adjacent, is 21/20, which means the cotangent value is 20/21. So I told you that I won't always give you all 3 sides. That's exactly what happens in example 2. In example 2, they say, using trig values to find the other ratios. They've given us the tangent. So we have to draw a right triangle. You can draw it anyhow you want, but it has to be a right triangle. We have to label theta, and I don't think I drew this right, so that's okay. I'll put theta up here. The reason I'm putting theta up here, normally I'd put it down here, but tangent TOA is opposite over adjacent. My opposite should be the longer side. Tangent of theta equals 5/2. Well, if this is theta, this is my 5, and this is my 2. If I drew it differently, whatever, it doesn't matter. I do have to find the hypotenuse, though. Well, this is a right triangle, so Pythagorean's theorem, a squared plus b squared equals c squared. 4 and 25 are 29, so c is the square root of 29, which I believe is not reducible. I just want to double check that I added that right. I'm like 99% sure I did. Yes, 29. So lucky you, we don't have to break down that radical, but unlucky you, we're going to have a radical in all of our answers. We're going to have to try to simplify them. So this is my triangle. I already know tangent, which means the easiest one to get afterwards is cotangent, because all I have to do is flip this ratio. There's one of the other 5, because it says find the exact values of the 5 remaining functions. Again, don't give a decimal answer unless they tell you to round. They're telling us to give the exact value. So for sine of theta, now that we have this defined, the opposite is 5, the hypotenuse is square root of 29. Well, that's unfortunate. We are going to have to rationalize this, but before we do, I'm going to do the cosecant because it's the reciprocal, and if this has to be rationalized, the reciprocal shouldn't have to be rationalized. Square root of 29 over 5 is the cosecant value. For this one, I'll rationalize the denominator by multiplying by square roots of 29 over square roots of 29, which means I'm not changing the decimal value, just the way the fraction is represented. This gives me 5 square roots of 29 over 29. If I could reduce the 5/29ths, I would. If I could break down the 29, I would have done that over here. So we've got 1, 2, 3. We have 2 more to get to our 5. We have to do cosine. Cosine of theta is adjacent over hypotenuse. So 2 over the square root of 29. I will have to rationalize this. However, before I do that, I'm going to write down the secant of theta, which is the reciprocal value. Square root of 29 over 2. I don't have to rationalize this one. It's good. This one I do have to rationalize. Multiply by square root of 29 over square root of 29, giving me 2 square roots of 29 over 29. Again, if the 2/29ths could be reduced as a fraction, I would, but it can't. So there are my 1, 2, 3, 4, 5 remaining trigonometric functions. Letter B. They've given us cosecant as 3 halves. Well, I don't know, I don't memorize that it's hypotenuse over opposite, so when I'm drawing my triangle, I can't even think that way. So I immediately say, wait, what's cosecant reciprocal of? It's the reciprocal of sine, which means sine of theta is 2/3. That makes it much easier for me to draw my right triangle because I know that sine of an angle is opposite over hypotenuse. Now I may have drawn my triangle wrong again because I think this will be shorter than this, but that's okay. Using Pythagorean's theorem, x squared plus 2 squared equals 3 squared. 9 minus 4 is 5, so this is the square root of 5. It cannot be broken down. If it could, I would break it down right here to make less work for myself when I do the 6 ratios. One of them was already given. We found one of them here. We now move on to cosine. Cosine of theta is adjacent over hypotenuse, which is square root of 5 over 3. This means that the secant will be the reciprocal value, 3 over the square root of 5. This one does not have to be rationalized. This one does. This gives us 3 square roots of 5 over 5. And the last trig values are tangent and cotangent. Tangent of this angle would be 2 over the square root of 5. We'll come back to that to rationalize it in a second. Right now I'm going to write the reciprocal value, which is square root of 5 over 2. That one's already rationalized. Come back up to this one and rationalize it. 2 square roots of 5 over 5. So you don't want to rationalize this and then flip it, because then I have to re-rationalize it, and I really waste a lot of time doing that. So if you see that one is not, one has to be rationalized, immediately find the reciprocal value, and then go back and do the rationalizing. That concludes example 2. Example 3 is getting back to the heart of what you did in geometry, which is solving the right triangles using Sohcahtoa. So when we use Sohcahtoa, we were asked to find the value of x. Oh, thank goodness, I don't want to find all sides. We sometimes are asked to do that. So I'm looking at this problem, and again, I write down Sohcahtoa. The good news is you won't really use cosecant, secant, or cotangent to solve the triangles. When you're trying to find a missing length or find missing angle measure, you will refer to Sohcahtoa. So you'll be using sine, cosine, or tangent primarily, just as you did in geometry. With respect to the 53-degree angle, I did not tell you which trig ratio to give me because I don't want the ratio. I want you to use one of these to solve for x. So notice the difference. Over here I said find the trig ratios. So you're saying, oh, okay, you want me to find these, here's their ratios, and I'll simplify them. Here, I'm not telling you what ratio. You have to figure out which one of these to use to help you solve the side. Well, with respect to this angle, make sure it's a right triangle if we're doing it this method. This is the opposite side, and this is the hypotenuse. So which trig function uses the opposite and the hypotenuse? Sine. So we have sine of 53 degrees equals the opposite over the hypotenuse. We set this over 1 so that we can cross multiply. This gives us x times the sine of 53 degrees equals 15. Please do not put the sine of 53 degrees in your calculator and write a decimal, because the moment you round, you start developing rounding errors throughout the rest of your problem. You should, as long as it's possible, not give a rounded answer until your final answer. So leave this as the function sine of 53. To solve for x, we're going to divide by the sine of 53. And almost all of you have calculators that will do this. So in our calculator, we're going to do 15 divided by the sine of 53 to solve for x. And make sure, because we are working in degree mode, our calculators are programmed to work in radian mode. In geometry, you went to degree mode and strictly worked there. In PreCalc, we work in both degree mode and radian mode. So you have to hit the math key on your calculator, hit the math key, mode key, hit the mode key. And for most of you, radian will be highlighted. There will be times in this unit where we will have to go into our calculator and highlight radian mode. But for now, we're working in degrees. So we will highlight the degree mode and hit enter so that it is the highlighted mode. Now I can plug this into the calculator and get the right value. 15 divided by sine of 53, is 18.78. They asked us to round to the nearest tenth, so this would be 18.8. Again, make sure that your mode is on degree. If you use radian mode, you will get a completely different answer. In this next triangle, we're asked to find this side. This side right here, with respect to this angle, it almost looks like the hypotenuse, but the right angle is here, so it's not. This is the hypotenuse. So that means this is the adjacent leg, and this is the opposite leg. And I can barely read that number, but I think it is a 9, so we're going to treat it as a 9. With respect to this angle, we have the adjacent and the opposite. Which trig function uses both the adjacent and the opposite? Tangent. So we have tangent of 21 degrees equals the, notice it's opposite over adjacent. So opposite over adjacent. So it's your tangent function over 1. We're going to cross multiply. We get 9 equals x times the tangent of 21 degrees. To solve for x, we will divide 9 by the tangent of 21 degrees, and we'll do it like that, exactly like that in our calculator. We're not going to put tangent of 21 in first and round and create rounding errors. So everyone, when they plug it in like this, should get 23.44, which rounded to the nearest tenth is 23.4. And they don't have any units. If they had feet or inches, we'd put that on it. That is using Sohcahtoa to find angles. Using Sohcahtoa to find angles. So here, we know that reciprocal functions are cosecant, secant, and cotangent. So if you ask for ratios, we can give those. But here, we're only using sine, cosine, and tangent to help us set up and solve the problem. Now this brings us to inverse trig functions. Inverse trig functions are different than reciprocal trig functions. I'm really hoping that you covered this in geometry, but some of you may not have, and I don't have time to cover it as well here. You can come see me if you want to see a chart of values, but basically sine, cosine, and tangent are functions. When we do this, it is a function of the angle. The angle is the input. So if you put the angle inside, it tells you that for certain triangles like our 45, 45, 90, the sine is going to be 1 over square root of 2, which we rationalize, but your calculator knows the decimal value of 1 over the square root of 2 to be 0.707. So if I do sine of 45, there's the exact value that's been programmed in. It doesn't matter the size of the triangle. If this triangle was 10 times as big, well, 10 over 10 square roots of 2, whoops, I don't like the way these calculators work, is going to be the exact same value. So this is for all triangles that have a 45-degree angle. For all triangles that have a 20-degree angle, if you put the sine in, it will reduce to the same function, no matter the size of the triangle. So when we use regular sine, cosine, and tangent, so I'm going to write trig for trig function, and we input the angle, the output is the ratio. So what we're actually doing, going back again to your geometry mind, is I didn't give you two triangles for you to set up a proportion to solve similar triangles, which you did in geometry. Instead, I said, hey, we know the angle, and your calculator knows the ratio of a similar triangle. So if you set up the tangent ratio of 9 over x, here's the decimal value it's equivalent to. But of course, we don't use that in our calculator. We cross multiply and do all the operations at the end. Well, there is an inverse function. If you use the inverse function, there's our notation. Remember, we have f of x versus f inverse of x. Makes a lot more sense to you than geometry students that this is the notation for inverse. Well, the inverse works in reverse. If you put in the ratio of the trig function, if that is your input, then your output is the angle. So if you tell your calculator, hey, I'm doing sine, tell me of 20 degrees, what's the ratio? It will tell you. If you say, hey, I have sine and I know the ratio and I want to know the angle, then you don't do sine, you do sine inverse. So let's take a look at that on here. With respect to this angle right here, I have the opposite and I have the hypotenuse, which you guessed it is sine. Sine of theta equals 14/16. I could reduce it. If they asked me to find the ratio, I would be expected to reduce it. They did not ask you to find the ratio, they asked you to find the angle. So, since I know the ratio for sine is this, the measure of the angle has to be, all I'm going to do is into sine inverse, I plug in the ratio of that I know is the sine ratio. So I hit second and then sine. So on my calculator, not just the sine key, but second and then sine to see the sine inverse of, if I plug in the ratio into the inverse, it will give me the angle. And it says round to the nearest degree, so this is 61 degrees. This angle is a 61-degree angle. In my next problem, with respect to theta, this is the adjacent and this is the hypotenuse. Sohcahtoa. I'm going to use cosine. Cosine of theta is defined as 5/12. That's the ratio. Now on the other side, I only asked for ratios, so you'd be done. But I'm not asking for the ratio, I'm asking for the angle. If you want to find the angle, you have to use the inverse. Use inverse of the ratio. Use the trig inverse function of the ratio. So theta will equal cosine inverse of 5/12. Second cosine inverse of 5/12 is 65 degrees to the nearest degree. This concludes clip 1 of 4.1. There is a second clip discussing angles of elevation and solving for all parts of right triangles that you can either watch today, or if I gave you directions, you could wait till tomorrow. It depends on what was listed in Skyward. Have a great day.